We are here at the 0 PM test site at Rastatt-Rauental Waterworks, which is about 30 kilometers from Karlsruhe in Germany. And here we are testing our hybrid treatment process to remove per- and polyfluorinated alkyl substances from drinking water. 0 PM is a research project funded by the European Union, which stands for Zero Pollution of Persistent and Mobile Substances. We also call them PM substances. The project combines 3 interlinked strategies to tackle pollution with PM substances, which is prevent, prioritize and remove. And we at TCW are developing methods to remove PM substances. The most prominent among these are the per- and polyfluorinated alkyl substances, or PFAS. In the Rastatt region, they've been dealing with extensive PFAS contamination for more than 10 years now. A huge amount of agricultural soil got contaminated. Some of the degradation products leached through the soil and have been detected in the groundwater for drinking water production since the year 2012. The PFAS contamination is currently treated by activated carbon filtration. The new EU Drinking Water Directive sets much stricter limits, particularly for the more hydrophilic short-chain perfluorocarboxylic acids, which are the most difficult to remove. And as a consequence, the water utilities have to replace the activated carbon in the filters much more frequently. This results in increased resource consumption and higher treatment costs, and is the reason why we are aiming to optimize the current treatment process. We are trying to do this by combining the current activated carbon filtration with the subsequent anion exchange treatment. And the activated carbon can retain the long-chain, more hydrophobic compounds for a longer period of time, but the short-chain, more hydrophilic compounds break through quite early. And these are then retained by the anion exchange resins. So the idea is that the anion exchange resins extend the operating time of the activated carbon by absorbing the short-chain compounds that the activated carbon can no longer retain. When in operation, the pilot plant receives the same influent as the technical plant, that is groundwater contaminated with PFAS. So the groundwater reaches the top of the activated carbon filter, which is operated in top-down flow with a filter velocity of about 10 meters per hour. And then we're testing 2 different anion exchange materials, one of which is a weak base anion exchange resin and the other one is a strong base anion exchanger of type 2. Both of them are also run in top-down flow. To ensure their continued use, the anion exchange resins need to be regenerated regularly. At the moment, this is about once every 2 or 3 weeks, but we're continuously working on optimizing our regeneration process. To enable an in situ regeneration at the waterworks, no organic solvent is used in the regeneration process, but only brine, so hydroxide or salt solutions. So basically our goal is to keep all materials in operation as long as possible before they need to be exchanged. In our lab we did all the work that was necessary to pre-select the materials that potentially could be used in the hybrid process. So we did a lot of adsorption and desorption test series with different materials, then discussed the results with our colleagues and then made a choice about which materials we want to test further. The most promising ones ended up in the pilot plant. We conducted batch experiments on a laboratory shaker in which we recorded sorption isotherms. The samples taken from our experiments and the pilot plant are analyzed in our analytical lab. And generally, the results so far suggest that the treatment process works. Using the combination of activated carbon and our weak base anion exchange resin, we've been able to remove PFAS and extend the operating time of the activated carbon while keeping the new threshold values for PFAS. And the next question will be if we can actually extend the operating time in a way that the whole process becomes economically feasible. And for this, we're working closely together with our 0 PM project partners, such as the colleagues from the Chalmers University in Sweden. In the end, we're hopefully all contributing to a more efficient and more sustainable water treatment in the future.